Last time we particularly went into the world of graphing them, right? We talked about graphing the sine curve, the cosine curve, and even the tangent curve. We saw how the sine curve is really just the y coordinates of the unit on the unit circle as you traverse around counterclockwise on the unit circle. So as you move around a full revolution around the unit circle, your angle of the terminal side with the positive x-axis is increasing from 0 to 2 pi. And as that's happening, your y coordinates will go up, become 1, then it goes down to -1, then goes right back to 0. So, oh yeah. So Felipe, definitely. Yeah, we can definitely go over the homework if you got any questions with it, for sure. And so yeah, I just wanted to quickly just go over what we've done. So cosine, the same thing, right? Cosine is really just the x coordinate. As you move around the unit circle, that's how the x coordinate changes. It starts from 1 and then it goes back down to -1 and it goes right back to 1. And then tangent of course is a bit different. It is still the graph of it still repeats itself, but it has vertical asymptotes in this case. And the one thing that we've talked about as well for all of these curves is the frequency, the amplitude, and the midline. So those are the period as well, the period, frequency, the amplitude, and the midline. So those characteristics are important to know for the sine and cosine curves. And the tangent curve doesn't really speak about, we don't really speak about frequency nor amplitude, but we do consider the period. So sine and cosine have a period of 2 pi. So after every 2 pi radians, you see one full curve, whereas the tangent requires just pi units. And then we talked about how we can, we can transform each of these graphs. We can perform transformations of the parent function, which is sine or cosine, and you get a new kind of sinusoidal function. So that's what we did last time. And we go on to the world of inverse trig. But before that, there's some trouble with the homework, so let's see what we can do about that. All right, let me pull it up. So Felipe, do you have a particular problem on the website? Homework for today? Yeah, okay, so we'll do 9, 10, and 29. Let's do that. Let me just pull it up. All right. So math 122. Let's see what's up. So number 9. Number 9. Okay. This is lecture. What is number 20 already? Wow, number 20. And then today is the 3rd, pardon me, of May. Okay, so we're going over homework number 9. In particular, we're going over number 9. So number 9, we have a, wait, is number 9, number 10? Yeah, number 9 and number 10 is very much the same idea. So the idea is what? Unit circle, right? This is my unit circle. What's my unit circle say? What's my center? 0, 0. What's my radius? 1. And what we're doing is we're dividing this up. We're dividing it, the pi, right? We're dividing pi, and this is what? Yeah, they call it the x-axis, the y-axis, right? We're dividing the upper half into fourths, right? So we divide this in half, and we divide this in half. We divide this in half, and we divide this in half. So we have a whole total, consider this a pizza pie, we have 8 slices of pizza, right? Okay. And this is the way it's drawn. And so they have this table. They have this table here. T represents, in this case, it represents the angle, okay? And then they want to know the terminal point. So they want to know what are the x and y coordinates when my angle is the one that's given. Or sometimes they give you the terminal point and you have to figure out, right? The course. No, they don't give you the. Yeah, they just literally just say, hey, fill out this table. So for example, when 0 is my angle, what is my terminal point? And I think we did this. We did this for, yeah. We did this already. I don't know if you guys remember this, but last week we went over the angles. We didn't do this exactly with the coordinates, but okay, I see. So the idea is, if you start at 0 degrees, what are my coordinates? If I'm right here, what's the coordinates here? Isn't it 1, 0? Right? So then isn't this 1, 0? That's like the straightforward one that comes right off the unit circle, comes right off. Okay, the next one would be what? Because now they divided pi into fourths. You see that? Or you can say they divided 2 pi into eighths. So what's the angle here? What's this angle here? 4, right? Okay, so the angle is pi over 4, also known as 45 degrees. But what do you know about 45 degrees? This is one of those angles, like I mentioned right here. We just talked about it, right? We know what is cosine of 45 degrees. It's rad 2 over 2. We know what sine of 45 degrees is. It's also rad 2 over 2. So what's the terminal point again? It's the x and y coordinate. Remember that, guys? So the terminal point is the x and y coordinate, which is equivalent to the cosine of the angle, comma, the sine of the angle. I know this is when you have to connect everything and put them together. Terminal point, cosine, sine, x and y coordinates, angles. It's the hard part is connecting all those characteristics together. But that's what we're doing. So in reality, what we're asking ourselves is, what is cosine of pi over 4 for the x coordinate, and what is sine of pi over 4 for the y coordinate? But we know that, or we should know it. So it's rad 2 over 2, comma, rad 2 over 2. And then the next angle is what? The next angle is right here, right? This is what? 90. This is pi over 2. What are the coordinates of the unit circle when your angle is pi over 2? Just look at the unit circle. The unit circle is 0, is a radius of 1, right? This is a radius of 1. So this portion right here would have to be what? 0, 1, right? And guys, this just repeats itself. But however, you have to be mindful of what quadrant you're currently in. So for example, in the next angle is what? It's 3 pi over 4, right? We're 135 degrees from the 0 degree mark. So it's 3 pi over 4. You can think of it also as 1 pi, 2 pi, 3 pi over 4, right? So we got 3 pi over 4. Now 3 pi over 4, because of the symmetry, guys, there's symmetry behind this. You see this? They got the same y coordinate, but my x coordinate is just negative, whatever this was. That's all it is. So now this would be what? Negative rad 2 over 2, comma, rad 2 over 2. Done. And then I just continue on. Pi is what? Pi is this point here. The terminal point associated with pi is right here, but this is going to be what? Negative 1 comma 0. Do you guys follow me? So this table should be almost it should just come off. It should just the values, once you know these values here, everything else is known. Just the sign is going to change. That's it. So the next angle after that, so you did 1 pi, 2 pi, 3 pi, 4 pi, now 5 pi. 5 pi over 4, then 5 pi over 4. You see this? It's the same as this point here, the same x coordinate, but now the y coordinate is negated. So, and of course, you're in the third quadrant, so both x and y coordinates are negative. So it's going to be negative rad 2 over 2, comma, rad 2 over 2, negative. And then we're almost there. So we got 3 pi over 2. That's 270 degrees. And that's going to be what? 0 comma negative 1. Then the second to last one, 7 pi over 4. Is this clear, guys? For those of you out there? 7 pi over 4 right here, right? This point right here, because of the symmetry, is just a reflection across the x-axis. So the only coordinate that's negative is the y coordinate. So it's going to be what? Positive rad 2 over 2, comma, negative rad 2 over 2. And then lastly, when you go all the way around 2 pi, obviously you just made one full revolution around. So this is going to be where you started from, 1 comma 0. So that's how you fill out this table. It seems like you're doing more than what you're actually being asked for. Chen, yes. You always want to simplify your fraction, but you should be able to recognize the equivalent fraction. So yes, understanding fractions, equivalent fractions is important, and we usually always simplify. Okay. So number 10 is the same idea. The only problem is that it's longer because we're dividing up pi into more slices. In this example, we did it into fourths. Now in the next one, number 10, we're doing it into sixths. So overall, we're gonna have 12, right? We're gonna have 12, still too big. We're gonna have 12 slices overall. So we have, I'm gonna divide it into sixths, right? Whoops. Okay, not the greatest drawing in the world, but yeah, somebody has their audio. Can you please, let me see, mute yourselves. There we go. Okay. All right, so here we are, right? In this case, we're dividing pi into sixths. So again, this is pi. So this would represent pi over 6. This is 2 pi over 6. This is 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. Do you guys see that? So pi over 6, pi over 3, which is 2 pi over 6, right? The equivalent fraction, you guys should be able to recognize that. This is 3 pi over 6, which equals pi over 2. This is 4 pi over 6, which is 2 pi over 3. This is 5 pi over 6. This is 6 pi over 6. This is 7 pi over 6. This is 8 pi over 6, which reduces to 4 pi over 3. This is 9 pi over 6, which is equal to 3 pi over 2. This is 10 pi over 6, which is equal to 5 pi over 3. And this is 11 pi over 6. And this is 12 pi over 6, which equals back to 2 pi, or 0. Do you guys see that? Pi over 6 is 30 degrees. We've done this. You guys, are you guys seeing the connection? We've done this. We know what it is, or we should know, right? Cosine of pi over 6 is what? Rad 3 over 2. What is sine pi over 6? A half. So I know my coordinates will be what? What are my x and y coordinates? Gotta make that table. So I got the t value, or the theta, and then I have the terminal point column. And then I have my rows, and I start with 0 degrees, or radians. And so then my first point will be what? 1 comma 0. Obviously, we just did that. Then the next one is pi over 3. So then the coordinates will be what? It'll be rad 3 over 2 comma 1/2. So guys, what we're doing is we're connecting all the column values for cosine, and then we're just pairing it with the values for sine. So if once you have that table that we have written before in last week, just connect them both. Put them in the same set of coordinates, but respectively in their correct x and y coordinate place value. Next one will be what? Oh, pardon me. This is pi over 6. And then the next angle will be pi over 3. And so on and so forth, right? Pi over 3 is 60. Remember at 60? These are just swapped. This is what? 1/2. And rad 3 over 2. And then the next one will be pi over 2, but we already did pi over 2, right? And even in the previous one, we already know this will be what? 0 comma 1. Are you guys following me? Hopefully now you see it's not as bad as you thought. It's really just putting everything together. That's all it is. Now, once you have this clear in your head, trig should not be a problem, or not as much as a problem as you once thought it was. So this is going to be what? 2 pi over 3? Let me just fill out 2 pi over 3. Then we got 5 pi over 6. Then we got pi. Then we got 7 pi over 6. Then we got 4 pi over 3. Then we got 3 pi over 2. Then we got 5 pi over 3. I'm almost there. 5 pi over 3. And then we got 2 more. Okay. 5 pi over 3. We got 11 pi over 6. And we got 2 pi. We know 2 pi already is 1 comma 0 because that's where we started. And then 2 pi over 3. Do you guys see the symmetry of a circle? 2 pi over 3 is directly across the y-axis of the point pi over 3. We know pi over 3 is what? 1/2 comma rad 3 over 2. But if you reflect it across the y-axis, what you're negating are the x-coordinate, So the x-coordinate will be what? It would be negative rad 3 over 2, positive 1/2. Do you guys see that? 5 pi over 6. 5 pi over 6, I am directly across the y-axis for pi over 6. So the x-coordinate again is negative, the y-coordinate is positive. So what's the x-coordinate? Oh, pardon me. This should be negative 1/2. Pardon me. This should be rad 3 over 2 because I am comparing 2 pi with pi over 3. So it's these here have to be the x-coordinate has to be negated for this point. And for this point, the x-coordinate is negated as well for 5 pi over 6. So it's negative rad 3 over 2, comma, positive 1/2, and pi would be -1, 0. So if you notice, these coordinates here, right? These values here are the reference angles. So once you know the reference angle, you know everything, every point around this particular image here. Because all you have to do is know where you are in the quadrants. That gives you the sign of your point, and then you refer to the reference ones, because once you have these, the other ones will be exactly the same coordinates. It's just the signs will be either positive or negative, and you have to figure that out depending upon what quadrant you're in. So for example, 7 pi over 6, right? I'm in the third quadrant, so all the x and y coordinates are negative. And 7 pi over 6 is, the reference angle is pi over 6. So if I know pi over 6, which I do, just negate all of them, and I get what? I get negative rad 3 comma 2 over 2 comma negative 1/2. Same thing goes for 4 pi over 3. 4 pi over 3, I'm in the third quadrant. The reference angle is pi over 3. Take 1/2 and rad 3 over 2, negate everything. And I got negative 1/2 comma negative rad 3 over 2. 3 pi over 2, we already know that. It's 0 comma negative 1. 5 pi over 3, I'm in the fourth quadrant. Only the x coordinate is negative. And 5 pi over 3, the reference angle is pi over 3. Pi over 3 is 1/2 rad 3 comma 2, rad 3 over 2. Negate the y value. So what do I get? I get 1/2 negative rad 3 over 2. And then finally, 11 pi over 6, reference angle pi over 6, negate the y coordinate of pi over 6. So negate it. So I got rad 3 over 2, comma negative 1/2. And that's how you complete. That's how you complete the table for 9 and 10. Any questions about 9 or 10? Is this clearer? Does everybody follow this? Like I said, if you guys understand this about the unit circle and how the x and y coordinates are repeated, right, with respect to the reference angle, you just have to know what quadrant you're in. If you understand that, then a lot of trig will make much more sense. Okay? All right, so if there's no other questions, we can move on to the last. Yeah, to the last two problems that people were saying that they had trouble with. And hopefully also you'll see that it's not as bad as it seems. I know, I always say that, right? I always try to make it seem like it's not as bad as it seems. But that's my job. My job is to make you understand something that previously seemed difficult. Okay, so I have a right triangle for number 29. I think we have the same numbers, but even if we don't, the idea is identical. So we have the hypotenuse is 6, the angle here is called theta, and the side opposite angle is 5. And of course, they're asking us to find all 6 trig ratios, which is very common to do. So we got sine of theta, we have cosine of theta, and then we have tangent of theta. We got cosecant of theta, but once you know sine and cosine, you know everything. Because then you know tangent, then you can know the reciprocals, which is cosecant. We know the reciprocal cosine function, which is secant, and then the reciprocal tangent function, which is cotangent. So really the idea is I need to know all sides of the right triangle. I only have 2. So this guy here is unknown, x, right? So what must we do? Pythagorean theorem, right? So then we got x squared plus 25 equals 36. Solve for x. X squared equals 11, so x will equal square root of 11. Of course, we got the plus or minus, but we know that it must be positive because we're talking about the length. So this is rad 11, and remember, it says find the exact values. So we want the exact values. It just means leave your answer as a radical. Because the moment you put it as a fraction, it's no longer exact, it's approximate. So what is sine of the angle? Well, the sine of the angle is opposite of hypotenuse, which will be what? 5/6. Opposite, right? This is opposite angle. So you can write this as opposite. This is hypotenuse. And this is the adjacent side. So then once I know that about sine, then what's cosecant? It's just the reciprocal, 6/5. What's cosine? Cosine is adjacent over hypotenuse. So that's going to be what? Rad 11/6. What is the reciprocal? It's 6/rad 11. Tangent. What is tangent? Tangent is opposite over adjacent. What is that? 5/rad 11. And of course, you can always simplify, rationalize this, right? Multiply rad 11 on top and bottom. So I got 5/rad 11/11. So either or should be correct. I can write it this way or I can write it this way. They're equivalent. And then I can just use this one here and flip it, and I got rad 11/5. So that's it. That's how we do number 29. And number 30 should be the same idea. It's the same idea. Okay, so let me know if you guys have any questions about number 29. Is this understood? And this is a common problem in trig, using a right triangle and only knowing two sides. To find a third side using Pythagorean theorem, you can't have a radical, and then just fill out the side opposite over hypotenuse, those different ratios, adjacent over hypotenuse. What it's mean? Oh, okay. So the last problem, right? The last problem is very similar. It's not identical, but it's similar. Okay. So one thing I want to mention to you guys is that mathematics is understood by doing problems. You understand how to do mathematics by doing it. I know it sounds kind of paradoxical. How can you know something? How do you know how to do something if you don't know how to do it? So the idea is this, guys. You have to start to make connections on your own. That's hard. So here we have so this angle, this symbol here, okay, just to give you guys some background, is they're Greek letters, right? We use a lot of Greek letters. So this is alpha, similar to our A in our alphabet, and beta, which is similar to B in our alphabet. Chen, that's exactly the right observation. What you notice is that sine of alpha is cosine of beta. Now, how do I know that? Well, what is opposite alpha? 12. What is the hypotenuse side? 21. So this will always be hypotenuse. Now be mindful of this. So let me put this as alpha here, and let me put this as beta. So 12 with respect to alpha is opposite. This is opposite alpha. But at the same time, this is adjacent to beta. Now, why do I care about that? Well, if you notice, sine What is sine of alpha? It's the opposite side, which is 12 over 21. But that's exactly the same thing as cosine of beta. And then you have to make the conclusion. You have to make an observation. I don't know if you see it yet. What is the relationship between alpha and beta? This is a right triangle, right? All the angles in a right triangle or any triangle add up to 180 degrees. This is 90. So what does that make alpha and beta? So this is a key observation, guys. Key observation among all of this. The key observation is alpha and beta are complementary angles. What that means is they add up to 90 degrees, or pi over 2 radians. So if that's the case, if alpha plus beta equals 90 degrees, then what? Then sine of alpha equals cosine of beta. That's a pretty big truth. Example. The first example that we can think of is, right, sine of what? 30 degrees. What is that? Isn't that a half? Right? Go back to that table that we did. Sine of 30 degrees, sorry. Sine of 30 degrees, pi over 6, is a half. What's the complementary angle of 30 degrees? Isn't it 60 degrees? What is sine of 60 degrees? I mean, cosine of 60 degrees, pardon me, is also a half. Do you see the relation? Whoops, just died on me. Guys, do you see the relationship between sine and cosine? So this equals cosine of 60 degrees. Put anything else. Put sine, for example, of 1 degree. What's the complementary angle for 1 degrees? 89 degrees. Cosine of 89, if you plug in your calculator, is equal to sine of 1 degrees. As long as these angles here add up to 90, they must add up to 90 degrees. If so, then this relationship holds. That's why it's written this way. If this is true, then this is true. So that's the key observation here, guys. So that's the first one. A. Part A is sine of alpha and cosine of beta. They're equal. They're the same. And I think your numbers, I think they might be the same, right? And so then we can reduce this to what? Divide both by 3 and I get 4 over 7. That's my final answer. And then what do they ask here? They ask for tangent of what? Alpha and cotangent of beta. So tangent of alpha is what? Tangent is what? Opposite of alpha, right? But what's adjacent to alpha? Isn't that something that we need to figure out? Isn't this x? I don't know this yet. Pythagorean theorem, right? So what's the Pythagorean theorem state? It states that x squared plus 12 squared equals 21 squared. What is 12 squared? 144. What is 21 squared? 441. X squared. Subtract. What does x squared become? What is 441 minus 144? Isn't that Do that real quick. 441. Isn't it 297? So what is x? The square root of 297. And 297, I think you can break this down. Yeah, you can break this down. So this is square root of 99 times rad 3. And then you can break that down, right? Yeah, you can break that down because this becomes 9 times 11 times rad 3, but rad 9 is x, is 3. So x is equal to 3, and then 11 and 3 are underneath the radicals, so this becomes 3 rad 33. That's right. So this here is 3 rad 33. So do you see tangent of alpha is opposite 12 over adjacent? What's cotangent of beta? Isn't cotangent just flipping it? Cotangent is alpha, is adjacent to beta, right? And this is going to be opposite beta. It looks more confusing than it is. So if you just stick with one, tangent of alpha, just stick with that. What's tangent? What's the opposite? It's 12. What's the adjacent side to alpha? It's 3 rad 33. If you reduce, what do you get? The 3 goes into 12 4 times, and I get 4 over rad 33. And of course, you can rationalize it, but it's okay if you just leave it the way it is. So another thing you should notice is that tangent of alpha equals cotangent of beta. That's another thing. So this is one of them, right? And then the next one is that cotangent, or I should say, tangent of alpha equals cotangent of beta. That's another one. That's another result of having complementary angles. And then finally, last one, we want secant of alpha, which equals cosecant of beta. So this is our third one. This is our third relationship. So secant of alpha equals cosecant of beta. So what is secant of alpha? Secant is adjacent, right? It's the hypotenuse over the adjacent side. So once I know cosine, right, which is exactly, yeah, it's exactly the reciprocal. Well, yeah, it's the reciprocal of cosine of alpha. So what's cosine of alpha? It's 3 rad 3 over 21. Secant is just the opposite. It's 21 over 3 rad 33, which is the same thing as saying cosecant of beta. What is cosecant of beta? It's the hypotenuse over the opposite side, which is exactly what the adjacent side would be to alpha. So all of this is just dependent upon what angle you're using. And then this reduces, right? 3 reduces, 7 reduces to 7. And I get 7 over rad 33. And I'm done. I'm done with my homework. Yay. Finished it. Is this better? Is this clearer? Yes. Yes. Good. Good. Any other questions, let me know. Yeah, that's the whole point of doing homework. The homework is supposed to clarify or solidify your understanding. Okay, so up until this point, we've done a lot of finding the values for reference angles. We've done graphs of trigonometric functions, sine, cosine, tangent. We've done transformations of it. We talked about the unit circle. We talked about the different ratios, sine, cosine, tangent, along with the reciprocal functions, cosecant, secant, and cotangent. We applied the Pythagorean theorem. We talked about the different special right triangles too, 45, 45, 90, 30, 60, 90. And so we've done a lot. And now we're going to go into also a very important aspect of trig, which is inverse trig. And this is when things get flipped on their head a little bit. So we're doing inverse trig. Now, in order to do inverse trig, we need to recall what are inverse functions. So we have to know what are inverse functions. And can anybody tell me what are the properties of inverse functions? What are the different properties of inverse functions? And I should say, before we even talk about the properties, does anybody know what is a prerequisite? What is the prerequisite for a function to even have a inverse, to even speak about inverse functions? What must be true about our function? Does anybody know? Okay, so the prerequisite, remember we talked about this inverse function stuff in the beginning of the semester, near the beginning, the first few, probably lecture 4 or lecture 5 or something like that. The prerequisite is that the function must be it must be 1 to 1. Remember this? It must be 1 to 1. What does the 1 to 1 mean? Does anybody remember? What does 1 to 1 mean? It means two things from that. 1 to 1 means that what? What kind of test does it pass? What kind of test does what does the graph that's 1 to 1 pass? It passes so Chen, that's right. 1x cannot have 2y, right? So there's only one y for each x. Only one y value is associated with each x value. So this is like the opposite of what, not the opposite, but this is like the applying the definition of a function in the where the x and the y values are swapped. So in a function, every x value is only associated to one y value. And now you're saying the same thing. Every y value is only associated to one x value at the same time. And that's right. It has to passes the horizontal line test. So if you don't have a one-to-one function, we can't even continue with this inverse function world. Now, what else do we know? We know that we swap the x and the y's, right? We swap x's and y's. In other words, the domain, our x values of f, equals the range of f inverse, the inverse function. The range of f equals the domain of f inverse. Do you guys see that? This is literally saying the same thing. It's saying switch the x and the y's. The second characteristic of inverse functions, so these are characteristics, sorry, I should write that, or properties. So properties. of inverse functions. Another property is that the graphs of inverses or of inverse functions are reflected across the line y equals x. And we've seen examples of this, right? Haven't we? Example. Let's say if my function is what? My function is e to the x. Then what's the inverse function of e to the x? It's ln of x, logarithmic function. If I were to graph this, e to the x looks like this. That's e to the x. And it crosses what here, right? It crosses the y-axis at 0, 1. Then what happens? What happens to the ln of x? Ln of x is just if you, let's see, if you draw a line, I'm gonna dash it, y equals x, and I reflect this graph across this line, y equals x, this is what I get. I get a graph just like that. And it crosses here now, we swap the x and the y's, 1, 0. You see that? That's an example of what it means for two lines to have, two graphs to be inverses of one another. The graphs of each other are just reflections across the line y equals x. You reflect it across that line and then you get the other graph. And then you can just notice with one of the point, right? We just switch the x and the y's and then we get a new one. That's what it means to reflect across the line y equals x. You switch the x and the y's. So you see all of these here are equivalent. And now the more important one for us will be the following. If we compose inverse functions with one another, we get back what we started with. Example. We're going to use the same thing again, right? When we had this property, when we have e, for example, to the ln of 2, that's 2. Because e and ln are inverses of one another. If we do ln of e squared, we also get 2 because ln and e are inverses of one another. So when we apply a function and we apply it to the inverse of that function, we cancel out the function and we get x. And the same thing happens if we switch the order. It's the same thing. So all of these three properties of inverse functions that we discussed in the beginning now comes right back to us, comes right back in full effect, especially when we talk about inverse trig. And this is important, this whole inverse trig idea. So far so good, guys. Remember this? Do you guys remember inverse functions? This has to be clear. Okay. So now once you have this, remember sine. We're gonna do sine, and we're gonna do all of them: sine, cosine, and tangent. So recall sine, recall graph of sine. I think we all remember sine, right? And of course, guys, this repeats itself, right? And this is what? Pi. This is 2 pi, right? This is 1. This is -1. Okay, so this is what we got. And then this is pi over 2. This is negative pi over 2. This is 3 pi over 2. So on and so forth. And what else do we know? We know that the domain is what? What is the domain? Domain is all real numbers. And what's my range? -1 including, right? So bracket -1 comma 1 bracket. And this is f of x, right? Graph of f. What's my function? Sine. All good? We know this stuff. We just did it last time. I want to know the inverse of sine. What's the problem? Is the graph of sine 1 to 1? Is it? How do we determine whether something's 1 to 1 again? It must pass the horizontal line test. What's the problem? The moment I draw one horizontal line, how many points of intersection do I get? Because it goes on forever, I have an infinite number of points. So then the observation is what? Observation, observe. Graph, or I should say, the sine function is 1 to 1 since it fails the horizontal line test. Do you guys see that? It fails the horizontal line test. But I still want to consider the inverse of the sine function. So what do I do? I'm going to make it 1 to 1. So let's make sine 1 to 1 by restricting the domain. So we're going to be restricting, quote unquote, the domain. What in the world does that mean? That means that I'm going to take from the whole domain, I'm going to take one interval, restrict it to one interval. Now, what we're going to do is we're going to restrict the interval between pi over 2 and negative pi over 2. And you'll see why. So let me draw this again. This time, I only care about pi over 2, negative pi over 2, and pi over 2. And what do I have? I got something like this. You see this? You see this? This is my new domain. My new domain, my restricted domain is what? Negative pi over 2, pi over 2. My range, however, is identical to the original sign. It's still -1 to 1. Do you see that? So this continues, of course. This continues. But if you notice, once I cut it, I have a strip or a slither or a piece of the sine function that attains all the values of the range. And now it's 1 to 1. Do you guys see that? It's 1 to 1. And now I'm happy. So again, this is restricted domain. This is the restricted domain. And let me just draw one straight line just to show that this passes the horizontal line test and therefore 1-to-1. Are you guys with me? Do you guys see what we're doing? We went from a sine function, cut it, got a strip of it. The range is the same. The domain is just cut up into one interval. Regardless, now I have a 1-to-1 function, which I can find the inverse of. And that's the important part. And we know how to find the inverse, right? Don't we? What do? We swap the x's and the y's. Or we reflect the line, the graph across the line, y equals x. When we do that, we switch the domain and the range. You see all of this, how we have to connect everything, put it together, and when we do, we get something new. So that's the inverse, guys. So let's talk about the inverse of sine only. The inverse of sine. So what do we know off the bat? We know the domain and range of it. Why do we know the domain and range of it? Because we know the domain and range of our function here. We switch the domain and range. So now the domain will no longer be pi over 2 to negative pi over 2 to pi over 2. It's going to be -1 to 1. And then what's the range? The range is the domain. Remember, we just talked about that. We just said it. And yeah, we'll talk about that notation. F to the -1 power is exactly what inverse is, right? We talked about that already. So this is going to be negative pi over 2 to pi over 2. Domain and range are swapped. Okay, what would the graph look like though? What's the graph? All the x's become the y values. All the y's become the x's. So this will become what? -1 to 1. This is pi over 2 to pi over 2. Guys, this is really, negative pi over 2. All the x's become the y's and the y's become the x's. Do you guys see that? And now once you have all of that together, where's pi over 2? This point here is what? Pi over 2 comma 1. This point is what? Negative pi over 2 comma -1. Switch it. Now I got what? I got 1 comma pi over 2. Switch the x and the y's, and this becomes what? -1 comma -1 comma negative pi over 2. Now, how do you graph this though? How would that look like when you graph it? When you graph it, it looks like this. Now you're like, wait, did you draw the same thing? I did not draw the same thing. Think about it this way, guys. Think about graphing sine the way we normally would graph it, right? Now think of doing the same thing, but now twist your head 90 degrees and draw a sine curve. You see that? When you draw the sine curve, it's like this now. It's like the spiral, the wave of the sine curve that was going once horizontally, now is going vertically. And when you take the strip of it, you see this? You see this? This is the sine curve, but if I were to continue drawing it, the sine curve is going vertically now. You see that? But I don't have the whole sine curve. I just have a portion of it. And this is my inverse sine curve. This is inverse sine, guys. That's what it looks like. It looks very similar, but hopefully you understand that this is like as if I was drawing the sine curve vertically, and this is drawing the sine curve, of course, horizontally. Now, what's the notation? So what's the notation for inverse sine? There's two ways you can write this, right? You can write this as the following. You can say y is equal to sine with that -1 as a superscript. This is not a exponent. Negative sine inverse of x. This is one way. Or you can write it as y equals arc sine of x. They say arc sine. So if you say arc sine or sine inverse, same thing. So this is the graph of arc sine. And I'll give you an example of how this works. So for example, if I give you sine of pi over 6 is 1/2, then what would be the inverse? How would I write this as an inverse function? This is very similar to what we did with exponential and logarithmic expressions, right? Well, remember, this is my x, this is my y. Switch the x and the y's. So now this will be my inverse, sine inverse of what? Of 1/2. So the y coordinate is 1/2, right? But in this case, it's my input now. 1/2 is associated with what value? Pi over 6. Do you guys see that? The x and the y's are switched or swapped. So now, what does sine inverse give me? Sine inverse gives me the angle. Normally, we need the angle, we plug it into the trig function, and we get a number between 1 and -1. Now it's the opposite. Now we plug in a number between -1 and 1, and the output will be an angle. And that's what we're going to be interested in now, finding angles. That gets pretty fun. Does everybody follow this idea of inverse sine? Do you see how this is like a little story going from the world of sine to now the inverse? And we're going to be doing the same exact thing for cosine and for tangent. Okay. And just one thing I want to make sure I say before I continue is that the range, right, they represent angles. So this represents angles. And this is important. This will be important as we move along. The range are angles, and angles, right, exist in the if you look at the unit circle, right? It's on the xy plane as well. So the unit circle, right? We got 0, we got pi over 2, we got pi, we got 3 pi over 2, right? And we got back to 2 pi, right? That's how we usually go around it. But the range here, the angles here are from 0 to pi over 2, right? Pi over 2. But 3 pi over 2 can be rewritten if you go in the opposite direction, right? If you go in the clockwise direction, this can be rewritten as negative pi over 2. So my angles that are produced from sine, the angles that are spit out by sine are angles in the first and fourth quadrants. That is important. So the range represents angles in quadrant 1 and quadrant 4 only. You will never get an angle from arc sine that's in the second quadrant nor in the third quadrant because of this. The angles are in this interval, negative pi over 2 to pi over 2, which represents the first and fourth quadrants. That may not mean much to you now, but it will mean much as we as we move along with this inverse trig stuff. Okay, any questions about this? I know you guys may have more questions, but right now it might not be the time. But let me know if you have any. But yes, so this is inverse of sine. Arc sine, sine inverse. Okay, now let's look at cosine. Remember cosine? So recall the cosine curve. What does the cosine curve look like? And this goes on forever, right? This continues on. This is 2 pi. This is pi, pi over 2, 3 pi over 2. This is 1, negative 1. This goes on. What do we know about the domain? Same thing, right? Negative infinity to infinity. What's the range? Negative 1 to 1. What's the problem? Horizontal line crosses it more than once. What do we do? We have to restrict. How do we restrict? So tell me, guys, what do you think? What would be the interval here? So in the last sine example, we restricted the domain between negative pi over 2 to pi over 2. But cosine is a little bit different from sine. So how would anybody, what would be your suggestion to cut this, to restrict the domain? How would you restrict the domain in such range is unaffected? You keep the same range. How would you cut it? Who would cut it in what ways? Does anybody see it? No? Nobody would has no way to cut it. So obviously, look, I wouldn't cut it this way, right? What happens here? My range is not 1 to negative 1. So the negative pi over 2 to pi over 2 cut wouldn't work. But what would work? Would this cut work here? No, it doesn't also include negative 1 to 1. But if you cut it from here to here, you see? It includes all the range of the values. So I'm going to restrict my domain. We have to restrict the domain. So restrict domain. So my new domain is going to be from 0 to pi instead. My range stays the same. Negative 1 to 1. And so when I graph this, I only have this piece. And guess what? It's 1 to 1. We did it. So it passes the horizontal line test. Passes horizontal line test. So what does that mean? It's 1 to 1. That's so restrict the domain of cosine. For cosine. Now I can speak about what? The inverse. Now I can speak about the inverse of cosine? What's the inverse of cosine? We switched the domain and range, right? So my domain is going to be -1 to 1 because that's the range of my original function. But now the range of my inverse function is the domain of my original function. So it's 0 to pi. And then what would be the graph? What would the graph look like? Again, my x's and my y's, they change, right? So this is going to be from 0 to pi. That's going to be my y values, since my x values go from 0 to pi, my x values. And then my y values originally now are my x values. So I'm going to have something like this. This is -1 and +1 here, like that. And now this point here was what? This point here is pi, comma, -1. This point here is what? 0, comma 1. So, so now you flip it. When you flip it, you get -1, comma pi. -1, comma pi. This will be my point here. -1, comma pi, because I'm switching the x and the y's. And then this will 1, comma 0. Because my original function was 0, comma 1. Do you guys see that? And then when I graph this, and then if you want, you can even include this point here. This point here is what? This is pi over 2, comma 0. So now I'm going to have here at pi over 2. And again, my x's become y's and my y's become x. And when I graph this, look what I get. I get the cosine curve as if I'm drawing it vertically. So this is horizontally how we draw the cosine curve, right? And if you draw this vertically like this would be the cosine curve, but I only want this piece of it. That's it. And this is what's called inverse cosine or arc sine. So my notation is y is equal to cosine inverse of x or arc cosine of x. So this is my new inverse function. It's inverse of cosine. And as an example, right, we can say what? Cosine of what? Pi is what? -1. So then if I write this using the inverse cosine of -1 will equal pi. And by the same token that we spoke about, these angles here, right, the range of my inverse cosine function represent angles. So these angles are represented in what? In the interval, represent angles in, so what are the quadrants between 0 and pi? Go back to the unit circle. Go back to what it would be like if I were to graph the unit circle. From 0 to pi, this represents all the angles in what? In quadrant 1 and quadrant 2 only. So the inverse of cosine produces angles that are in quadrants 1 and 2. The inverse of sine produces angles that are in quadrants 1 and 4. Again, these characteristics, properties of these inverse functions are important to know, to distinguish the difference. Any questions? Is this new to you guys? Have you guys ever heard about inverse trig before? Or is this the first time? Yes and no. Have you guys seen the graphs of inverse cosine or sine before? Okay. Yeah, so this stuff is pretty new. So take some time to assimilate this new information. That's okay if you guys haven't, that's okay. But now you have. So now you know what arc sine looks like. Now you know what arc cosine looks like. And now we have one more to go, which is tangent. And I think now that we get to tangent, I believe you kind of see how this whole story plays out. And it becomes a little easier now to figure out what is it that we're actually doing. Okay, so again, this is arc cosine, and this is arc sine, or sine inverse. Okay, let's look at so tangent. Remember, we talked about tangent, right? So now let's consider tangent. So recall tangent. Recall the tangent function. When we look at tangent, this is what we have. Remember we talked about right? We talked about the horizontal, the vertical asymptotes. So my domain here, what's my domain? My domain and my range. My range is all real numbers, -infinity to infinity. And my domain, remember, we say that it's what? It's a little weird. You could write it as an interval, but it's also kind of weird to write it as interval because you have we have an infinite number of horizontal vertical asymptotes. So we say that this cannot be what? X cannot be anything that is an integer multiple of pi over 2. But what do I care about again? I care about the fact that I want the inverse of such a function, right? But you see this? What's the problem? It's not one-to-one. So we have another scenario where the original graph is not one-to-one. But we want to make it one-to-one. So what do we do? What did we do? What have we done? We restrict domain. Now I think the interval that we're going to restrict the domain for is kind of telling based upon the graph. So it was a little bit harder for sine and cosine if you've never done it before to know exactly what to restrict. But here, I think it's obvious, or more obvious, as to what interval I should choose. So what interval do you guys think I should keep in order to create a one-to-one tangent function? Is it apparent based upon the graph? That's right, Tiffany. Pi over 2 to pi over 2. That's right. Because the moment you have this piece here only, I got all of them just repeated. It just repeats. So might as well just restrict it to that. So then my restriction is the domain is negative pi over 2 to pi over 2. My range is still identical. It's still negative infinity to infinity. You see that? And just keep in mind that the domain does not include pi over 2 nor negative pi over 2. That's why we have the parentheses, because this is a vertical asymptote. So now look what I got. I got exactly what I want. I got the piece of tangent that represents all of the range. And it's all I need. All I need is this piece here. Okay? And now what do we do? What do we do after this? Once I have the restricted domain, once I have the fact that it's one-to-one, it passes the horizontal line test, it passes it because it only goes through once, right? One-to-one, it passes the horizontal line test. Then we swap the x and the y's. Here we go. Here we go. We swap the x and the y's. All my x's become y's. All my y's become the x's. So my domain and range is also switched. My domain here would be, okay, and let me just say that this is the inverse of tangent. That's what we're doing. We're dealing with the inverse of tangent. So my domain here is negative infinity to infinity. What's my range? Negative pi over 2 to pi over 2. My vertical asymptotes, remember, think about logarithmic functions. They have vertical asymptotes. The inverse is exponential, so it's horizontal asymptotes. So my vertical asymptotes become horizontal. And it's the inverse function of the tangent function going from vertically downward to vertically upward. It's going to look like the same idea, but now horizontally speaking. This is y equals negative pi over 2, and this is y equals pi over 2. This is x, this is y. Beautiful, 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 beautiful. And then what do we know about tangent? You can plug in anything for tangent, inverse tangent. And the angles here are what? Angles. So this represents angles. In quadrant 1 and quadrant 4. And what's my notation? My notation is y is equal to tan inverse of x, or y is equal to arc tangent of x. We did it, guys. We did it. We took the sine, cosine, and tangent functions that we know. We split it up. We spliced it into segments that represent the range. We reflected it across the line y equals x. We swapped the x and the y's. We switched the domain and range. And we find the new inverse trig function. So now we're going to be concerned with the angle, finding the angle. Normally we're given the angle and we find the values of what the angle would be. Now we're doing the opposite. We're giving a value and we want to find the corresponding angle. And that's the main objective now. Okay. All righty. So this is a lot of stuff, guys. I know it's a lot. All right. So now that we have that in our collection of the numerous kinds of functions that we can even speak about, let's start a little bit slow. So now we're going to evaluate inverse trig. So evaluating inverse trig functions. Okay, so first one, what would be sine inverse of 1? I'm going to give you a couple here. Cosine inverse of 0 and tan inverse of rad 3. So sine inverse of 1, think about it this way. Sometimes thinking about it in the regular way, right? Regular meaning not sine anymore. So sine inverse of 1 equals something is equivalent to saying sine of that something equals 1. So what angle do you guys know, should know, that when I plug in for sine gives me 1? What would you plug in here for sine? What angle? 90 degrees. That's right. And if we want 90 degrees, right? What is 90 degrees as radians? It's pi over 2. So sine inverse of 1 is pi over 2. Cosine inverse of 0 is I don't know. Rewrite this using the original cosine function. So cosine of the given missing angle has to give me 0. What angle for cosine gives me 0? We should know this as well. And it's the same one that we just saw above. Cosine of, no, not 0. Cosine of 0 is not 0. We'll talk about that. We'll talk about that right after we do tangent. So let's do cosine inverse of 1. So guys, that's why you have to know that table that we did with the cosine and sine, the reference angles. You got to know that through and through. So this also will be here. This also will be pi over 2. Right. What's tangent? Tangent inverse of rad 3. What is that? Well, think about tangent of one of those reference angles, right? Which one of those reference angles gives me rad 3? It's not 30, Chen. Rad 3 over 3 is 30, but just rad 3 is not 30. It's 60. This should be 60. But we're producing this in radians. So radians is becoming more of the preferred unit. So it should be pi over 3. So tan inverse of rad 3 is pi over 3. Are you guys following me how we go from one to the other? Now cosine inverse of negative of 1. Cosine inverse of 1. What is this? Same thing as saying cosine of, I don't know, equals 1. Cosine of what angle gives me 1? And that's when you say, Chen, what do you say? Cosine of, now it's 0. Cosine of 0 equals 1. So since cosine of 0 equals 1, then cosine inverse of 1 equals 0. And guys, this is what we're doing the whole time. Whole time. We're basically just rewriting what we already know, and we're just rewriting it in the opposite way. We care about the angle that's produced. And in the original way that we've done, we cared about what we got and what it produced after we got the angle. But now we're getting it the other way around. Now our value that we're producing is the angle, not the input anymore. Okay. And now let's spice things up a bit. What happens if I got sine inverse of negative rad 2 over 2? So what does that equal? Be careful. Think about sine of what angle produces negative rad 2 over 2. Think about what is rad 2 over 2? Sine of what angle gives me rad 2 over 2? Think about that first. We did that, right? For the homework problem that we were doing, that homework problem number 8 or number 9. Number 9, right? Rad 2 over 2, right? 45 is rad 2 over 2. That's right. Pi over 4. Okay, Felipe, that's right. You got that negatives, right? So be careful. So hold on with that thought. Hold on. Sorry, it's a lot of scrolling. So rad 2 over 2 is related to what? Pi over 4. But remember what we said about inverse sine? The angles that are produced are only in angles 1 and 4. That's it. And we're dealing with a negative y value. The negative y value must mean I'm in quadrant 4. Because if I'm in quadrant 1, everything's positive. So this angle is 45, but it's the angle whose reference angle is 45 in the fourth quadrant. So my reference angle is 45, or pi over 4, right? But I'm in the fourth quadrant. I have two ways to write about that, right? Either I can write it this way, that angle, which is what? 7 pi over 4, or I can write it as a negative angle, which is negative pi over 4. And of course, the range, remember the range, guys. Remember what the range was for sine inverse. That's why this is important now. Sine inverse, right? What's the range? Between negative pi over 2 and pi over 2. So this angle here that I just got, this angle here, 7 pi over 4, is not in the range for sine. So it must mean it's negative pi over 4. And that's why, Felipe, when you said you got negative 45 degrees, that's the reason why. That's the reason why you got negative. So now this becomes a bit more tricky, right? When the numbers aren't just positive anymore, when they're negative, we have to know, first of all, what inverse trig we're dealing with, and then know how to find it based upon what quadrant that those angles are produced in. So for sine, the angles are only produced in quadrants 1 and 4. For cosine inverse, the inverse of cosine, the angles are in quadrants 1 or 2. Now, is tangent for quadrant 3? Yeah, tangent is positive in quadrant 3, but still, if we go back to inverse tangent, look what we have. Our range is not quadrant 3. So then this is where the ambiguity arises. This is where it can get sometimes confusing to some people. It could be strange. What happens for angles in quadrant 3? And that's when we have to be extra careful. We have to be extra careful with this. So we'll get there with the inverses. So I'm gonna show you the next few also with negative inverse functions. So for example, cosine of inverse of negative a half. What is this equal to? And tan inverse of negative 1. What is that equal to? Okay, so we're gonna take this step by step. Cosine inverse of negative a half. So what I tend to always do is forget about the negative for now. Just worry about what it would be if it were positive. Cosine of a half, inverse of a half is what? What is that associated with? What angle is cosine inverse of a half associated with? Pi over 3, right? 60 degrees. But what do we know? So I'm going to erase this. What do we know about inverse cosine, right? Didn't we say that it's between the range, guys? The range, isn't that between 0 and pi? So cosine of a half, right? Of positive a half deals with what? 60 degrees or pi over 3. But that's if I'm in quadrant 1. Everything is positive. The x values are positive. But in quadrant 2, my x values are negative, which means cosine is negative. So cosine of negative 1/2, right, has to be what? 2 pi over 3. Or 120 degrees. That's why, Felipe, you get 120. Do you see that? So cosine of negative a half is the angle in the second quadrant whose reference angle is pi over 3, because that's associated with positive a half. But I have negative a half, so this should be 2 pi over 3. So guys, all of this is really just going back to the unit circle. It always comes back to the unit circle. If you have the unit circle, all of this makes sense. If you don't have the unit circle in your head, if you don't understand why we care about the unit circle, this stuff becomes almost indecipherable. But go back to the unit circle. That's like home base. Okay. If you don't know anything at all, but you know the unit circle, you can reconstruct all of this stuff, all of it. You can reconstruct the sine, cosine graphs, and then with the inverse trig, all of it just makes sense. But you must have the unit circle clear. Then now let's look at the next one, tan inverse of -1. So first of all, what is tan inverse of 1? Tan of what gives me 1? Pi over 4. That's right. So tan inverse of 1 is pi over 4, right? Pi over 4. Everything's positive, guys. Everything's positive pi over 4. But I don't care about positive. I care about -1. And again, tan inverse what? Tan inverse produces angles in quadrants 1 and quadrants 4. So I care about what angle, really. The angle in quadrant 4, because that's where my value is negative for tangent. Quadrant 4, where the reference angle is pi over 4. Remember, this is pi over 2. This is negative pi over 2. So what would be the corresponding angle for inverse of -1? Tan inverse of -1. It's not going to be pi over 4, but it would be rather negative pi over 4. Again, the unit circle, guys. The unit circle. The unit circle is embedded here. Think about the unit circle again. Think about number 9. I have the unit circle, right? This angle here is pi over 4. This is 7 pi over 4, or equal to negative pi over 4. Remember, tangent is only exists in quadrants 1 and 4. So if this is +1, this will be the -1. So the unit circle, guys, the unit circle. Okay. All right. Okay, then next. So once we start getting comfortable with that, let's do some more inverse trig stuff. So now we want to simplify. Simplifying expressions using trigonometric functions. Expressions. Inverse trig. So here we go. What's sine of sine inverse of 1/4? So this goes back to that property of inverse functions that we talked about, that last property, right? If I have an inverse function and I'm applying the inverse of that function, if I'm applying inverses to one another, what happens to the inverses? What happens to those functions when you apply one inverse to the other? What happens? They cancel out. That's right. So you can try it yourself in your calculator. You can do sine inverse of 1/4 and then take sine of that. You get 1/4 because they cancel out. That's why we apply these properties, guys. That's why these properties hold for any kind of trig function, whether it be any kind of inverse function, pardon me, whether it be inverse functions or logarithmic exponential. It applies to all of it. How about the next guy? So for example, cosine of cosine inverse of 2/3. We have cosine inverse. Obviously, they cancel out. We get 2/3, right? Obviously. Next, what about um, tan of tan inverse of 5? Then you're like, oh, this is too easy. You made it too easy. Now we know it's 5 because they cancel out. Doesn't seem to be too hard at all, right? Okay, what if we do the same exact thing for this? What's sine of sine inverse of 5? What is it? That's what. Why did you get no answer, Felipe? So you have to understand why you don't get no answer. No, you don't get 5, guys. You get actually undefined. And now you may be like, wait, what? Why is it undefined? Well, how do we start this, right? If we were to do it on ourselves, by ourselves, how do we start this? First of all, wouldn't we first evaluate sine inverse of 5? That's the first thing we would do, right? Step 1. Sine inverse of 5. But then think about it in the non-inverse way, right? Think about this as sine of some angle giving me equal to 5. Is this possible? Do we know an angle that we plug in sine, we get 5? Isn't sine between -1 and 1 always and forever? Isn't the range of sine 1 and between 1 and -1? So 5 is impossible to get. This is impossible. This statement is impossible because 5 is not in the range of sine. So this is a preposterous expression. So you have to be very careful. This looks easy, right? Sine, sine, oh, sine, cosine, oh yeah, they all cancel out because they're inverses, but that doesn't always make sense. It doesn't always make sense to do that. So you have to be mindful of the domain and range. This is when you have to be very careful with the domain and range for sine inverse, sine cosine, regular cosine, tan inverse, and regular tan. This is when it becomes very important. And you'll see this becomes very important as we do a little more of these kinds of expressions. So for example, let's continue with this. Okay, something like this. Look, something like this. Now we'd have the inverse first. Sine inverse of sine of 3/4, 3 pi over 4. What do you think this is? What do you guys think this will produce? Sine inverse of sine 3 pi over 4. What's your first initial reaction? 3 pi over 4, right? But is it 3 pi over 4? Think about it. Sine inverse. What is the range of sine inverse? Didn't we talk about that? The range of sine inverse is Negative pi over 2 to pi over 2. Quadrants what? 1 and 4. What's 3 pi over 4? Isn't 3 pi over 4 quadrant 2? But sine inverse can never produce something in quadrant 2. Be careful. So what I would do is I would take this step by step. This would be sine inverse of what? What is sine of 3 pi over 4? Just worry about this first. What is sine of 3 pi over 4? I'm in quadrant 2. Sine of 3 pi over 4 in quadrant 2 is what? Rad 2 over 2, positive. And now look at this. What's sine inverse of rad 2 over 2? Or in other words, right? Sine of what angle gives me rad 2 over 2? And we should know this. 45 degrees, right? But what is that? Pi over 4 radians. So be very careful. You can't just cancel stuff out, even though it seems as though you can, because the domain and range of sine and cosine tangent. You have to be careful. And I'll leave you with that. All right? Okay.